I've established a case where we can't tell the difference between signal delay, phase shift, and polarity. But the difference is there, we just can't see it. One reason is that we're only considering part of the sine wave. We can only see two of the wave's 3 dimensions. This is easily envisioned by considering a helix or spring. The sine wave is only one perspective on the 3-dimensional signal. Let's look at the signal processes again with this in mind. With signal delay, I'm sliding the spring down the time axis, always to the right. With phase shift, I'm rotating the stationary spring about the time axis, always counterclockwise. A polarity reversal inverts the spring, like it's wound in the opposite direction. Neither the arrival time or phase are affected. Clearly, there's a difference between these 3 processes, even if it isn't apparent on a scope. The difference becomes more obvious if we shorten the sine wave. A pure 1 kHz sine wave must be continuous. If I truncate the wave, the bandwidth is increased. This is an important point, so I'll demonstrate using REW. Shown is 50 milliseconds of a continuous sine wave. The time domain is shown at the top and the spectrum at the bottom. A sine wave of long duration has a very narrow spectrum. If I truncate the wave in the time domain, the spectrum is broadened. This truncated sine wave is called a tone burst or wavelet. Using the spring example, signal delay moves the wavelet down the time axis. The all-pass filter rotates the wavelet about the time axis, and a polarity inversion produces a mirror image of the wavelet. Clearly, there's a difference between these processes, and wavelet analysis makes the difference obvious. I'll use the signal generator in REW to produce a 6.5 cycle wavelet, and I'll use the wavelet to measure the response of the DSP. I'll check the box to route the signal generator back to the timing reference on the sound card and hit play. And I'll set up channel 2 to trigger on this signal. This establishes a time 0 reference. I'll drop a marker there so we don't forget where it is. With the timing reference established and marked, I can hide it. I'll then bring back up the DSP control blocks, each one bypassed. And then I'll unmute the signal passing through the DSP. Now we can take our closer look. First, there's some latency between the DSP signal and the reference signal. The latency can't be removed. It's a byproduct of digital processing. It affects everything that passes through the DSP. With that established, let's look at how each processing block affects the signal, starting with the delay. Adding delay slides the wavelet down the time axis. The phase and polarity are unchanged. The all-pass filter rotates the wavelet about the time axis. This advances its phase without changing its arrival time or polarity. And the polarity block inverts the signal without changing its arrival time or phase. So, there's an obvious difference between these processes for transient signals, like wavelets, music, and speech. The 3 tools in our alignment toolbox are signal delay, phase shift, and polarity. I'll put all 3 to work in the next video.